Okay, so hello guys. Hopefully everyone is here now. We're just gonna go ahead and get started. So first thing is first, I want to remind you guys about Up Owl Night. Information about that was on or in my email today. Along with that, I also put the What to Study guide in there and reading days tutoring information. So I accidentally only sent you guys one of my reading day hours. I will have another one, and so I'll send out a correction email later today. But I just want to let you guys know I will be doing Tuesday and Wednesday. But again, I'll send out a correction email. So Up Owl Night, in case people haven't heard or read about it yet, is going to be Wednesday, December 9th. It's essentially going to be a day where the class office holds tutoring and final exam review sessions for a bunch of different classes. So please be sure to check the schedule if you're taking any other classes that are supported by academic support services. But for Orgo 2, we have a couple people who are holding tutoring and final exam review sessions. It's basically going to be going on from 3 p.m. to 10 p.m., I believe, for Orgo 2, so you can drop into any session. I will be having my exam review. It's going to be 2 hours long, and it will be from 3 to 5 p.m. on December 9th. Katrina will have her final exam review session from 7 to 9 p.m. And then, as I mentioned, there will be tutoring hours throughout or in between those times as well. The reason I am talking about those two final exam reviews, though, is because Katrina and I will be splitting the semester in half, essentially. So I will be covering the first half of the semester, and Katrina will cover the second half. We just thought that would be more convenient for you guys so you get the most out of your time, I guess. And we understand that people may not be able to attend both of the reviews, so we will be recording and they will be posted like always. It might just take a little bit of time because they will be so long. So I believe that's all I had for Up Owl Night. Any questions, comments, concerns? So yes, my session will be posted on the YouTube channel. I believe Katrina's will just be on Canvas, but I'm not 100% sure. She probably has more about that in her email. I also should mention tutoring sessions for the reading days and for what's it called? The Up Owl Night. Those are just drop-in, so you don't have to make a appointment ahead of time. So the links to those sessions will be posted on the Up Owl Night website that I included in my email. So if you have any questions about those or you want to check the schedule or anything, follow that link and you'll have a whole bunch of information on there. Any other questions, comments, or concerns? No? Okay, cool. So let's just jump right in to the material then. Basically what we ended off with last week was the Hell-Volhard-Zelensky reaction. This was part of chapter 18. We have pretty much 2 more reactions to go, and then we're going to look into the chapter 19 reactions. There's only 2 of those, so we're going to go through them like really quick. I'm just going to give you guys a brief summary about them. We don't believe that they will be on the exam, but we haven't had a chance to talk to Dr. West yet, so I'm just going to give you guys a quick little summary about it, just in case, but we won't spend too much time on it. Any questions, comments, concerns about past material? Anything you guys want to look over? Anything you want me to like repeat? Someone said, have we gone over LDA reactions? No, we have not. Okay, so we'll go up here just for one more second. So I just want to review like the general stuff. I know it's been a while since we've looked at organic chemistry. We've had such a long break. So let's remind ourselves in halogenation and all these chapter 18 reactions, we're doing enolate chemistry. So essentially we're going to take a hydrogen off of the alpha position and we use that new anion to attack and attach something to that position. So essentially, the enolate is going to be our nucleophile, and in the case of the halogenation, Br2 was the electrophile. And at the end of the day, all we did was add a bromine onto that position. In the case of base, we know we add multiple times. In the case of acid, we only add one time. So this is going to be super, super similar to the alkylation now, because we will again create the enolate here. That will be our negative charge. It will act like our nucleophile, and we're going to add something to that position. So I kind of gave away the first question I was going to ask you guys, but what do you think we do with this thing? What do you think it can act as? It could be a nucleophile. If you treat it as a nucleophile, where would it attack? The carbonyl, cool. And have we seen any reaction like that before? So someone said yes. Where have we seen a reaction like that? First of all, before you even tell me that, what would we call this guy? We've learned about it. It has a special name. Ethoxide, yes, that's technically correct. That would be the name of it, but the one I'm looking for, someone said, is the alkoxide. Exactly. So the alkoxide is what compared to an alcohol? Or what is its relation, I should say, not compared. Yes, awesome. It is the conjugate base. So what reaction have we seen in the past where the conjugate base of our alcohol acted like a nucleophile and attacked our carbonyl? I'll give you a hint. Think chapter 16. Yes, so think about the acetal-ketol reaction, right? So we've done this before where it would come in and attack here, right? We would make the hemi, and then we could go on if we had a base if we had an acid, we could go on and form the ketol, right? So a lot of students will kind of get confused and do that reaction and get this answer and forget about this little green guy right here. So I'll leave this here for you guys so you can still see it. That's one of the options that could have happened, right? But at this point, we would have nothing else to do because this alkyl halide can't really react anymore. There's nothing else for it to do. So what else could this be? Think about that little thing we always say, anything with a negative charge can be a what or a what? A nucleophile or a base, exactly. So in this case, let's try out it working like a base, and I'm going to do that in blue. So what hydrogen can we take away? Because I don't see any hydrogens on a heteroatom. What else is acidic enough? What do we think? And alpha hydrogen. Cool. We've done this a couple times, but we have 2 alpha positions, right? Let's say alpha 1 and 2. Which hydrogen are we going to steal? 2, and remind me why again, please. Why is alpha 2 better? Yes, awesome, because it forms a more stable double bond, aka it has more substituents. Perfect. So I'm going to go ahead and draw these hydrogens in pink. And as we said, it'll act like a base. It'll steal that hydrogen. We make the enolate. So, bam. Negative charge. Now what? I'm going to let you guys think for a couple seconds and try and come up with what could possibly happen next. Yes, so we got one person who says that we could... Okay, well, we got a couple different things, so let's go through them in order. So one person said that we could form the double bond, which is true. We could definitely bring this over here, form the double bond, and bring those electrons back up here. But that resonance structure is more stable. So in order to kind of react, we're going to keep it with this resonance structure since it's the more reactive one. And I can repeat that. So since this is the more reactive resonance structure, we're going to not form the double bond because then that would kind of stabilize it and it won't want to react. So instead, as someone else said, we can do like an SN2 mechanism where we can attack here. And then what happens in SN2 when we attack? The chlorine will leave. Awesome. All right, so you already know what I'm going to say. We have to count our carbons. Let's not make silly mistakes. So we have 1, 2, 3 carbons. So we would get, this is staying exactly the same. We still have our hydrogen, and it's not important to draw out. I just like to give it to you guys. And then we have 3 carbons. And before I draw that new carbon chain, is there any chance that we can do any kind of rearrangements? No, cool. So we're just going to add 1, 2, 3, and it would be linear. Sorry, I'm reading something in the chat. So someone asked a really good question about the mechanism in the textbook, and basically how it's kind of drawn a little bit differently, or they do a couple different steps. So as I kind of said before, you can do it either way. So the textbook is obviously right. The way I do it is just a little bit simplified, I guess, or it's more straightforward, so we don't have to go through as many steps. So yes, the textbook is correct, but this is also a correct way of doing it, if that makes sense. Okay, cool. So we're going to go ahead and cross out this guy. And if you guys notice, every time I do a reaction or we do a concept, do a new concept, I keep bringing up old stuff, and you might be thinking, we already did this, let's get that over with and move on. But it's very, very important that we go back and we make connections, and you guys remember old concepts, because on the exam, if you just see this, you either might not see this, or you might just see, oh, okay, I know that this is a ketol reaction, and go ahead and do that. So, does it make sense why we can't go this way and we would only go this way in the reaction? Yes? Okay, cool. Any questions, comments, or concerns? So one person asked, so if the propyl chloride wasn't there, the ketol formation would be favored. So exactly, if there was nothing here, we only had the alkoxide, we would be able to do this reaction. So let's say we had just this right here, no propyl chloride. Would we stop at the hemiketol, or would we go on and make the ketol? What do you guys think? If this was all we had. Okay, so we kind of got a 50-50. So explain your reasoning, please. So one person explained, they said hemi, it would stop at the hemi, and it's because the base catalyst does not react again. And so the answer is correct, but the reasoning is a little bit shaky. And I only say that because in this case, this is not a base catalyst. This is just your nucleophile. So in this case, we actually wouldn't have a catalyst the way it's drawn, the way the reagents are drawn. But you're still correct, because if we don't have any kind of catalyst, we stop at the hemi. And if we have a base catalyst, we stop at the hemi. The only time we go all the way to an acetal or a ketol is with what kind of catalyst? Acid, exactly. Cool. And then someone had asked me to go back up here, so I'm going to zoom out slightly. I'll let you take a look at that, and then if you had a question about it, I'll give you a second to ask that. Okay, cool. You are very welcome. Alrighty. So we're going to go on. Wait, hold on. And no worries, someone asked another question. Did we already cover the Hell-Wohlhard-Zielinski reaction in the last SI session? So yes, we did, but we can go through it really quick in summary because I know a lot of people weren't there last week because of Thanksgiving. So do you guys want to really quickly summarize this mechanism? You know what? I made an executive decision. It's okay. Let's just do it. So this reaction, we essentially have two different conditions. So we can either do it with Br2 and PBr3, or we can do it with Br2, PBr3, and H2O. So I'm going to erase this, pretend you didn't see it. So in this first case, we have Br2 and PBr3, which is kind of a weird mix because Br2 we saw all the way back in PBr3 we saw all the way back in chapter 11, and now Br2 is chapter 18, right? So let's remember, what does PBr3 do? Yes, so PBr3 is going to turn OH into Br. And then someone said that I covered these in my tutoring session. I did cover them in tutoring, but I'm almost positive I also did it in SI. But it's okay, we're doing it now, again, either way. So then, what does Br2 do? What reaction did we learn about where we do Br2 as a reagent? Halogenation, cool. And in a halogenation, where do we add the bromine? On an alpha carbon, cool. Oops. Awesome. So the same exact thing is going to be true, I'm zooming out, over here. The only thing we add is H2O. And H2O can do a bunch of different things, so we're going to come back to it and see in this reaction what it's going to do. So in the first case, if we don't have water present, we're going to first use PBr3, and we're going to turn OH into Br. So we go from what functional group to what functional group? Yes, carboxylic acid to an acyl bromide or an acid bromide. Those are synonymous essentially. So yes, now that we created our acid halide, we have our base that we just created, right? Because we got rid of this OH. And so now that steals an alpha hydrogen, creating the enolate. And then we essentially just perform a halogenation and we get 2 bromines added to our molecule. One of them took the place of the OH, the other one took the place of an alpha hydrogen. If we have H2O present, and the first couple steps are exactly the same. So if we have H2O present, it's going to act almost like an acid catalyst at first. We're going to steal a hydrogen, we're going to protonate the carbonyl, and we formed a better nucleophile. And now that nucleophile can attack the carbonyl carbon and kick off the leaving group. And remind me what kind of reaction mechanism that's going to be. And you can be pretty broad, it doesn't have to be super specific. Exactly, so this is going to be a nucleophilic acyl substitution. So what chapter was that? 17, perfect. So essentially, kick off leaving group, add nucleophile, we end up with a carboxylic acid. We just have to deprotonate. And so our final answer looks almost the same as this case, except we turn the acid halide back into a carboxylic acid. And then, yes, specifically, we would call this a hydrolysis, which is just a more specific name for the nucleophilic acyl substitution when you add an OH. Any questions? I know we did it kind of fast because I already had it drawn out. But do you guys have any questions, comments? And I can also zoom out so you guys can see both of these on the same page. I'll give you guys like 10 seconds to take a picture or whatever, and then if you have any questions, you can either unmute or type it in the chat. And I am also going to send you the attendance sheet link, so please do that whenever you have a second. Okay, so we're gonna go on to the last 2 reactions. And I really love these reactions because they look super scary and disgusting and terrifying, but they're not. They're actually not too bad once you start doing it. So, first thing is first, this is called an acetoacidic ester synthesis. So what do you think the product is going to be? Just by the name. Ester. Exactly what you would think, and that's actually wrong, which is wonderful, right? Because why would the name make sense? A lot of students actually get tripped up on that. That's why I ask and I kind of make the joke. So if he asks you like a concept question about the ester synthesis, just remember this is different than what we learned in like chapter 12 about making and breaking esters. That's not going to be the same thing. So the reason it's called the acetoacetic ester synthesis is actually because we are starting with an acetoacetic ester. So this guy right here is called an acetoacetic ester. And you do have to know that. And the next reaction here is a malonic ester synthesis. And these two mechanisms are going to be exactly the same. The only difference is the starting material. So this one is an acetoacetic ester. What do you guys think the name of this will be? A malonic ester, perfect. And the difference is that, the acetoacetic ester is an acetone with an acetic ester, and they're attached together. And the malonic ester is two esters attached together. So one thing I want to point out before we do the reaction, I'm going to zoom into the acetoacetic ester, and then we're going to do that whole thing and then go on to the next one. So let's go here. The way I say this, never mind. All right, so what is the, you know what, I'm not going to ask it like that. What's the relationship, sorry, I don't know why all of English left me. Where are these connected in relation to one another? Alpha, beta, gamma, delta, etc., etc. What do you guys think? So I'll say it one more time. So these ketones, or these carbonyls, are what relation to one another? Alpha, beta, gamma, delta. Ooh, okay. So we got a couple different answers. So let's remember, what is an alpha carbon in relation to the carbonyl? Directly adjacent, exactly, the one right next door. So this one I'll write in blue. This one is alpha. This one is alpha. So that would mean this is beta. And then if we go the other way around, this one is alpha, this one is beta. So that would mean these two carbonyls are beta to one another. And it is important that you remember that. Any questions about that? I know I said it kind of weird, I apologize. But again, just remember that these carbonyls are going to be beta to one another. All right. So if we look at this reagent, or this set of reagents, I should say, what does this look like? Or like, what do we think it'll do? Could be a nucleophile, and I'm guessing you're saying that because of the negative charge. So let's draw it out. Right, that's what we have. And then PHCH2Br, that is just a fancy way to say, or not a fancy, more like a mean way to give you that. So I want you guys to tell me what this is called. Is this a benzyl halide or a phenyl halide? Benzyl, exactly, because it has that little bend in it. Cool, just making sure you still remembered. All right, so this is actually kind of a familiar setup, right? what reaction did we see in chapter 18 that has a similar set of reagents? The alkylation. Super. So we have this thing with a negative charge that can act like a base, and then we have some kind of alkyl halide underneath. So in this case, we have two alpha hydrogens, or two sets of alpha hydrogens, I should say. How do we know which one to take? Let's call this alpha A, and this can be B. Which one do you guys think we're going to steal? Ooh, okay, so most people were saying B, but then one person said, would we have to like think about less steric hindrance? So in this case, we care less about steric hindrance and more about acidity, even though it kind of makes sense to think, oh, this is kind of a bigger base. You might have to consider sterics. For the purposes of this class, we don't really have to worry about that. So you guys were correct. We are going to take from this position. So I'm going to go ahead and erase all this stuff just so we have like a clean slate. So besides that position being more substituted, there's another reason that one is super acidic. Can anyone think of why that position would be super, super acidic? Resonance, exactly. So we kind of have double the resonance because it can be resonated to both carbonyls. Awesome. All right, so I'll stop my talking and let's do the reaction. So first thing is first, we steal that hydrogen and give those electrons to the carbon. And since the reagents take up so much space, we're going to go like this. And so here, nothing much changed except we formed what? What special name does this intermediate have? One person said it, but I want a couple more people to say it. When we have a negative charge on that alpha carbon, what is that intermediate called? The enolate. Super. Okay, cool. So now that we have the enolate, we also had our alkyl halide. So as you guys told me before, we're going to do an SN2-like reaction. We are going to attack here, kick off the leaving group. And remember, this carbon should not disappear in the next drawing. And what I say, or what I mean by that is, a lot of people will just do this, but we know that's not right because we have to have that extra carbon in there. So we have this. And then someone asked, if the negative charge became a double bond and the pi bond went to the oxygen, would we still call that the enolate? That's a great question. So yes. If we did this, why do I choose such long molecules? Right, we brought the double bond here, and we gave a negative charge to the oxygen. These two are resonance structures of one another, so they are both called the enolates. So if he asked you which of the following is the enolate, both are correct. But if he asked you which one is the more stable resonance structure, we know that this is going to be more stable because oxygen holds the charge better than carbon does. Questions on that? So now at this point, we have product A. Oh, my bad. There was a question. I just missed it. And so, yes, the question was, so this one would be less reactive, hence why we choose this one. Yes, exactly. So this is the more reactive form, so we tend to just keep it that way. Plus, we draw less steps than if we had to do like bam, bam. But you would get the same answer either way. Don't ever apologize for asking questions. I love questions. All right. So now that we have A, let's draw our reagents for the next step. We have NaOH and H2O. Okay. So now we have a reagent that we've seen a bunch of times. This is just OH minus with water, right? So we're going to have to kind of think through this next step. Let's think, what is there to do here? Like, what possibilities do we have? We could do a nucleophilic acyl substitution. Cool, so if we did that, we would use this OH as a what? A nucleophile. Perfect. So then what would H2O do? Or what would it act as, I should say? Acid catalyst. Perfect. Okay. So if we thought about this more of a chapter 18 view, what could we also think of doing? Like, what could this base do instead of acting like a nucleophile? Yes, we could steal an alpha hydrogen. But now think one step further about why that would make no sense. What would we add to that alpha position? Exactly. All we have is H2O, so we would end up just adding another hydrogen. So we definitely could do both of these, like in a solution, both of these things would be happening. But us as students who are trying to get like a final product, it would not make any sense to do enolate chemistry at this point, because if we stole this alpha hydrogen, we would just replace it with another hydrogen. So I'm going to go ahead and agree with you guys. Let's do a nucleophilic acyl substitution. And what are the steps to doing a nucleophilic acyl substitution? What's the Rosemary method? Cut off the leaving group, which is... Whomst is our leaving group? Yes, awesome. So this guy, or this thing I should say, is our leaving group. We already said that the oxygen is our nucleophile. Are we going to get rid of a hydrogen in this case? Ooh. Can we get rid of a hydrogen in this case? Ooh, okay, so we got one yes and one no. So let's go through it. If we got rid of this hydrogen, we would just add an O, right? And then if we added an O, or let's go ahead and draw something first so we're not just speaking to the air. I'm not even going to attempt to draw that. I'm just going to write a pH. Okay, so at this point, we add an O. If we got rid of the hydrogen, we would end up with an O minus. but we don't like that. So we're actually going to go ahead and keep the hydrogen in this case. And so if we are ever unsure about the hydrogen canceling rule, most of the time you will cancel the hydrogen, but just make sure to look at your final product and think like, does that make sense or is this an exception? Alrighty, so up until this point, we did a lot already. We're already at product, or I should say, yeah, we can call it product B. Any questions up until this point? No? Oh.
I have a quick question.
Yes, what's up?
So we used the enolate at the top because it was more or less stable.
This one?
Yeah.
Yes, okay, so that's a great question. We're going to use this resonance structure because it's less stable and it's more reactive. And what was I going to say? Oh, yes. The reason it is more reactive is because oxygen is better at holding a charge than carbon is. So this will be a much stronger nucleophile or base than this would be. So we also got another really great question. Why wouldn't the acid anhydride be the leaving group? I thought that was more reactive. That's a great question. So let's first remember what an anhydride looks like, right? So we have one carbonyl. What is attached in the middle? An oxygen. And then we have this group, right? So the anhydride is kind of like the flip-flop of this. So instead of having an oxygen here in the middle, the oxygen is out here. So I don't really know how to say this, but like they're just two completely different things. So this couldn't be removed because it's a carbon-carbon bond. And yeah, I see how this could get confusing. There's so many things that look alike. I totally understand where you're coming from. But that's a really good question. Okay, so at this point, I'm going to give you guys a hint. You actually haven't seen heat in these reactions before, so it's going to be something different. So let's walk through it together. Sorry for zooming in and out so much. So I'm going to redraw B, so this, on a new line. And we're going to do something called a decarboxylation. So I'm going to zoom in again. And write decarboxylation. And that will be the last step of this reaction. So the first thing we're going to do is rotate this bond. And when we do that, all we're going to do is redraw this molecule. So we haven't done any reaction. All we have done is bring the OH up and tilt this down. So all we did is rotate this bond right here, which I'll draw in purple just so you guys have a reference point. And so now, I'm also going to draw this hydrogen up here, and it'll make sense in a second. So does everyone follow how I redrew it? Because I know it can be really hard to visualize sometimes. Good? All right. So with this hydrogen hanging out over here, it can go close to this carbonyl, And we can get this effect called hydrogen bonding, which would mean that these electrons will actually kind of attack and attach to that hydrogen. So we end up stealing the hydrogen from the OH. So if that were to happen, where would those electrons go? The electrons from this bond. To the oxygen on the right. Awesome. So, bam. And now we're actually going to do kind of almost like in Friedel Crafts. Do you guys remember how we like did a circle of arrows and all the bonds broke and were made at the same time? Do you guys remember what that's called? When all the bonds are broken and formed at the same time? Starts with a C. Yes, a concerted reaction. So we're going to do a similar kind of thing here. And so instead of drawing like 6 arrows, we're going to just draw it in 3. And so these electrons will go to the oxygen, and the oxygen will actually use them to form a double bond right here. So we're going to just straight away draw the arrow going from there to here. And then we encounter a problem here because we already have 4 bonds, right? So that's actually going to make this purple bond break, and those electrons will go here. Is everyone following the arrows so far? And so, yes, exactly. This is what happens with the heat. So heat is going to cause a decarboxylation, which is what we're drawing right now. So if we follow all these arrows, we see that on the left, we end up with a bond to the oxygen, which made a new bond to the hydrogen. And we have a double bond right here. And attached to that double bond, we have this. And of course, a hydrogen. We could have also flipped this around so the hydrogen was pointing here and this group was pointing here. It makes no difference. And our second product is going to be O, double bonded now to that carbonyl carbon. Coming off of that, we have an O. And it would kind of look like that the way it's drawn. But just to make it pretty, we're actually going to redraw it like so. And so now, does that look kind of familiar to you guys? And I'll move it over a tiny bit. Does this kind of look familiar? What if I write out the condensed formula? CO2, exactly, cool. So CO2 is going to be our byproduct of decarboxylation. It's always going to be formed. We don't really care about it. What we really care about is this, right? So what form is this product in? Let's think of, okay, you guys got it. I didn't even have to explain. You are totally right. So this is in the enol form. So this is a reaction. This is where it ends. But I just want you to be aware that we can go back and forth between the ketone and the enol form. So I'm going to go ahead and write that. And just so I have enough space, I'm going to move this CO2 up here. CO2 is not going to change, it's just going to be a side product. So we can perform a tautomerization and go from the enol to the ketone form. And so when we do that, all we're going to do is take this hydrogen and bring it down here and move those electrons up here. And we can actually go through and do it if you guys have questions. If not, we can also move on though. And so someone asked, would we still be using acid or base to interconvert? So yes, you would have some acid or base left over in the reaction that you could use. The main point is just for you guys to know that like both of these can exist in solution. You can go up here and figure out like what's left in solution. I think it would be OH minus. Okay, and then I'll zoom out for you guys. And someone asked, does Dr. West count the final, wait. Okay, so someone said, does Dr. West count the final exam review extra credit for accuracy or completion? That's a great question. I believe he is still counting it for accuracy because that's how he's always done it in the past. Yeah, until I hear otherwise, I'm going to say it's accuracy. And then someone asked how many extra credit points it is because they saw it's only 1 point on Canvas. So I think he made a typo. I still haven't been able to talk to him, so I don't know for sure. But I'm pretty sure once you click on the extra credit, it says 10 points. And I believe that when he sent you guys the notification, he forgot the 0. So I still think that it's 10 points. But again, I haven't been able to talk to him yet. Almost positive it's 10 points, though. You are very welcome. Okay. So we will do the last reaction. On Wednesday, it's going to be very fast because it's almost the exact same thing. But yes. Oh, and then someone asked a great question. So they asked, is this going to be a racemization or just the interconversion between the two? So we are not going to be doing a racemization because this isn't actually a chiral center since we have 2 hydrogens. So this won't be a racemization. It's just going to be a tautomerization. That's a really great question, though. You are very welcome. Okay, guys, I'm going to send the attendance link one more time. I will stay on for a couple minutes to answer any questions, comments, concerns you guys might have. But you're free to go for the day. Bye-bye.
Rosemary, I have a question about the grading or like the point system for this class.
Yes.
So on his syllabus, he said that there's like 30 points of weekly assignments, but if I'm counting the points right, there's only 20 right now. So we're like missing 10, and I don't know if he's just gonna like cut the total of 500 points to like 490 or like what's going on with that.
So yes, I've actually been thinking the same thing because I also got a lot of people asking if he's going to add more weekly assignments, and I think at this point it's too late to do that since it's the last week. I think he'll just cut that out and make it 490, but that's one of the things I'm going to be asking him about in our meeting. So I will send you guys an update about it. But yeah, I believe he would just have to cut it out I don't think there would be another way to do it.
Okay, thank you. And one more really quick question.
Yes.
The I know we're only covering like one or two reactions from chapter 19, but he assigned chapter 19 Orion, and like, do you know if that covers the entire chapter or just those two like reactions?
So it's going to cover the whole chapter, unfortunately. And
Okay.
don't quote me on this because sometimes he changes his mind. But usually he'll just leave chapter 19 as extra credit for the Orion.
Oh.
Not always, but most of the time, especially if he's not able to cover a lot of it. But as far as we're going to cover and the exam will cover, or maybe I don't have it. Oh, yes, I do. So these are the only things we're going to cover from chapter 19. So for the homework, I know there's lots of different ways to go around the Orion homework. It's not really relevant to the exam. So I would just stick with that and only kind of focus on the aldol and Claisen condensations, if that makes sense.
All right, thank you so much, Rosemary.
You're very welcome. Bye-bye. And
Bye.
then, sorry, go ahead. Someone said, do I think you guys have enough time if you start studying now? Yes, I do. So as long as you guys are kind of going back and reviewing old stuff and not completely skipping it, I think you guys have more than enough time. Obviously, don't wait till like the night before or like 2 days before. But if you pace yourself, 2 weeks is like more than enough. You're very welcome.
What an amazing session.
Oh, thank you. Wait, let me stop recording.